What are we talking about? We want to detect outliers, identify structures, and find interesting spots. What does that mean? The questions that we are asking is everything fine with my images? Where are the interesting differences between groups? And this can be a rather complex question because you might not only have two groups. Typically we have a couple of groups for different levels of certain parameters, of certain factors. And at the end you want to have a reliable statement about which of the spots shall be identified, because following up certain spots takes time. With respect to delta 2D, we are talking about step 4 in our recommended workflow. It is about analyzing expression profiles. This step is part of the workflow as implemented here and is based on the previous step, detect and quantify spots, which has been covered by the last webinar that has been held by ourselves in June, and it was about detecting and quantifying spots, and the basis of this about normalization, background subtraction, and other aspects of spot detection and spot editing and so on. If you would like to listen to this past webinar, we have recorded it and presented on our website in the Academy area under webinars. As I mentioned, the basis for today are complete expression profiles as we have created them in the last webinar, and this is based upon our unique approach which saves time and increases reliability because there are no missing values. There should be no missing values anymore within such kind of data view, heat map, or in quantitation tables. The tool that we are focusing on in delta 2D is the analysis window, which contains a number of statistical methods. Some of them will be mentioned in this webinar, and you can access this by pressing the Analyze button in any kind of statistics table. As you might know, delta 2D comes with a statistics table, and you can open since delta 2D 4.2 or 4.3 a number of different statistics tables according to your needs, including the groups that you like to be included. And for each of this table, this Analyze button is available, while there's only one possible analysis window open. It will be reopened with the new data if you click it from another table. So this is the window, the analysis window, and let's go ahead. Why are we doing all this? Are biological systems deterministic? If they are, why do we need statistical analysis? Well, in fact, if they would be deterministic systems, then we would have a certain quantity and would observe this same quantity all the time, whenever we measure, of course, under the same conditions. If we could control conditions properly, then we would if these systems would be deterministic systems, then we would face always the same quantity and for any observation. However, it's not that easy. We have stochastic processes, and that means the data is not just one data point which would be observed all the time, but it's distributed bell-shaped typically, or that's what we expect at least. That means the same parameter is observed over time with a certain mean and a certain standard deviation, and this is then modeled by bell-shaped distributions. If we face that, then we have to deal with testing, with statistics, and that's why we need experiments with replicates, for example. The experiment that I will use tonight, or for you today, this morning, is a cell line experiment. We have two factors. One is controlled by running different cell lines, a control and 3 treatments, and we have 3 points in time when we take samples, and for each combination of cell line and point in time we have 4 replicates. That means we have 4 times 3 times 4, 48 samples, which are separated on 24 digests. Of course, an internal standard ran with this in this experiment. In delta 2D it's looking like this. We have the 4 cell lines, a control, and one treated with treatment 1, another with treatment 2, another with treatment 3, and we have the 3 points and times, and for each such factor combination we have 4 replicates. More general remarks about statistical testing. Statisticians always say that a certain null hypothesis is tested. This null hypothesis is something that we don't really know. It can be true or false, and we observe data to then just have an estimation of whether it's true and false. So if it's really true, then all your processes are just random, all your results are just randomly distributed, and there's no real impact of a certain condition. If the null hypothesis is false, then there is a discovery there is a change in the data, and that means you should find it. Actually, sometimes we accept a null hypothesis and reject a null hypothesis depending upon the data that we have. So if we accept the null hypothesis and the null hypothesis is really true, then everything is fine, and the same is true for rejecting null hypothesis. If the null hypothesis is false, then everything is fine. There's no error. However, we can make an error if we accept the null hypothesis. We say there's no change, but in fact there is a change in my biological system. Then there is a discovery and I don't see it. On the other hand, the null hypothesis might be true and I reject it. I think there is a change while there is none, and then we face type 1 error, and that means I follow up this data, I want to publish a certain protein maybe, while there's no change at all, and this is then a false positive. Let's have a look in biological context. As I mentioned, if we don't, if we accept the null hypothesis while it's false, then we miss a discovery. This is not a real problem because we just publish something that could be published, but this is not something that is bad for our reputation. But if we publish a false positive, then we have wasted time and also money, and then we publish a protein where there is no change at all. That's why statistical testing makes sense and is important. But it's only possible if we know that the data quality is fine. And one aspect of data quality is to check whether the gel images are fine. The gel images and of course the quantities on them. And for this we can, for example, use the PCA. We have explained PCA in a previously held webinar in detail, so maybe you want to check out this. PCA is trying to cluster our data, in this case the images, to groups with respect to their similarity. It's not a clustering, a real clustering, it's based on the data and all the spots on the images, and then depending upon their similarity they are grouped together, or in other words, we find a projection in this data space where all these data is as neighbored as possible, where the distances are very small, where the variation is very small. And if it's resulting like this, where all the different image data is then nicely separated so that the replicates are separate groups here, then everything is fine. And then you can see easily outliers. For example, if a red spot would be in this yellow group, for example. Another possibility to find out whether the data is well reproduced is running hierarchical clustering, and this means that we iteratively combine those objects, that means those images which are most likely to each other, so which are neighbored. And so in this case, where we have 5 such objects or images in experiment, then we would check each of the possible pairs, measure the distance between the 2 objects within a pair, and then take this pair where the distance is the smallest. And then we create a cluster of these 2 partners. In the next step we have a look On the remaining possible pairs, now P1 and P3 are considered to be one object, and the distance between P1, P3 and P2, P2 and P4, P4 and P5, and all the other possible pairs is measured, and again those that are closest are clustered together. In this case, P4 is most like P1, P3. There's no smaller distance between another pair of objects here. Continuing with that until this graph is ready, results in such a view where we have different levels of clustering, and at the lowest level, of course, we have the highest similarity. Let me show this in delta 2D. Here we go. In the light table, which is looking like the screen that I showed in my presentation, we see that we have 4 replicates for each combination. Here in the name of the group, we see this is the control group 0 minute factor combination, control 30 minute factor combination, and so on. In the warping setup, we can see that there is a large number of standard images shown in gray connected to the respective G200, G300 images and warped to a central standard, and this is done for 2 parts of the experiment, and they are bridged with certain fused images, but that doesn't matter. It's just a certain kind of setting up this graph. This results in the quantitation table, and the quantitation table includes values for all the images and all the spots, and it should be complete, so there shouldn't be a missing value when doing this with the delta 2D workflow. With our recommended workflow, we have also published it in 2007, and you can review that. It's available on our website as well. Having these complete expression profiles, we can then press this Analyze button, and then the data is standardized. In case of multiplex experiments, it's logarithmized also, and then the statistics window is appearing. Just a second, it takes a moment to transfer the data to this window. Now let me first change a certain parameter, because otherwise it does not fit on my screen. Here we go. Now we have 48 images forming 48 columns, and each row is representing one expression profile, and the spot quantities are translated into colors. The color gradient is shown here on the top. It's ranging from -6 or 7 to a +5 or 6, and high values are shown in orange, lower in blue, and the medium values are shown in black. So then let's start with the PCA. I want to have a PCA not for the rows, for the proteins, but for the samples, the gel images. I press OK, and then delta 2D will calculate this PCA. Here we go. I just hide the text boxes here, and I would just like to point to make you aware of the clusters here. I hope that you can hear me still clearly. The clusters here, for example, the dark blue spots are close to each other, the yellow spots, the red ones, the cyan ones, the green ones, and so on. So this is looking pretty nicely, and not only that the smaller groups are close to each other, also the different the cell lines are clustered together. So here you can see the shades of blue for the cell line control, and here are the green ones together for the cell line treatment 1, for example. This is a 3D view. I can now rotate it so that you see that this is looking rather nice. You can see maybe that here these two groups of green are close to each other, so the similarity within this cell line is very high. Now let's have a look for hierarchical clustering. I would like to cluster not the genes but the samples, and we recommend that you do this just at the beginning for quality control, and later on you can, for any test, use, and that is nice to do this, to cluster for the genes and for the proteins, but not for the samples, because then you change the order of the rows, of the columns, sorry. And if you change the order of the columns, then it will be difficult to interpret expression profiles. You should keep them then in the order as they come from delta to the other views, from the quantitation table, for example. In this order, you know then the expression profiles, and if you always cluster again the images, then you will always get a different order of columns, and this doesn't make sense. I press OK and get now this clustering, hierarchical clustering for the images. And as you can clearly see here, there is a line with the colors of the groups. All the images belonging to the same group are clustered together on a low level of the clustering. That means all the 4 dark blue ones are clustered together, or the yellow, light blue ones are clustered together, and so on. And not only that, also those belonging to red, green, and yellow, this is the treatment 2 cell line, are clustered together on a higher level. And this is very nice to see. Otherwise, either the images would be mixed up, maybe an orange image would appear with the green group, if it would be similar to a replicate there, or groups would be mixed between cell lines. And all this is not the case here. We can see that not only groups but also cell lines are separated very well, and this is a very nice sign for our quality. If it appears that some images will have left their groups, then you should review the image carefully and then maybe also decide for ignoring it from the analyzer, excluding it here. Then you could just exclude it from the quantitation table and start this analysis once again. Coming back to my presentation, we would then, based on good images, we know the images are fine, there is no problem or outlier image, then we want to find changes of interest, and a very common test for this is the t-test. And the question is there a difference in expression levels between a group A and a group B? And the null hypothesis is the means of the two groups are the same. And for ANOVA, where you can analyze multiple groups, not only 2 but multiple, of course varying only 1 factor, you shouldn't mix up the variation of 2 factors there, so you should only change time but not the cell line if you apply the ANOVA test. For ANOVA, the null hypothesis is the means of expression levels in all groups are the same. That means there is no change whichever pair of images we look at. So the null hypothesis can be rejected if there is a change. And for ANOVA, if there is a change for a certain single pair of groups. And ANOVA doesn't tell us which group. This is the disadvantage of ANOVA. We can use it for multiple groups, but the disadvantage is we don't know where the change is then. Then finding changes of interest should not only be done on the background of just quantitative data, you should also be aware of the number of rows that you analyze. The multiple testing problem is something that is more and more considered, but of course it should have been considered from the early beginnings. Multiple testing means the more expression profiles you analyze, the more random findings with significant data will be among your findings. A certain example, maybe you find a better one, but I would just illustrate it with this one. If you all play lottery and no one of you knows the numbers in advance, then the more people play it, it will be more likely that anyone will win just by random. And this is more or less the same here. The more drawings we do, the more different expression profiles we study, the more likely it will be that we will see a certain strange combination of expression data which is just due to the stochastic processes, due to the bell-shaped distribution of data, and see that there is a difference while there is no difference coming from biological changes. And this multiple testing problem should be dealt with. There are methods for it, and I will show them on one of the next slides. Furthermore, you should use replicates. As an example, if we just have two certain populations, one is the control and one is the treatment, and each includes 15 individuals, then we might only, if we just take two replicates, we just measure two of them, then we might, for example, just by random, take these orange circled values. And then we would say, okay, there's no change at all between control and treatment. They all have the same level. However, if you look at the other data points, there might be a change. We are almost sure there's a change. So if we by random would select the green ones, then we would come to the conclusion, okay, there's a change, and this would be okay. While the real means really have different levels in the two groups. So it's just random which two of the 15 you select. And the more values you measure, then the more stable your conclusion will be, and the more unlikely it will be that you draw the wrong values. Another example, here we don't have obviously a change between control and treatment. Well, if we now choose these two values, then we would think, okay, there's a change where there is none. And this is the type 1 error. We would have a false positive finding. We consider there's a change where there is no change. We would detect the protein, we would identify it, we would do a lot of further stuff to really learn about this protein. And at the end we might learn, before publishing hopefully, that this can't be true. There is no evidence that this can be true. There must be an error. The more problematic it would be if we don't get it and publish this protein. On the other hand, if we just by random take the green ones, then we would have a good interpretation of the data, but it's just random which of the two we get, and that means the more replicates, the more stable your conclusion, the better your conclusions will be. In this example here, the mean is completely identical between the two groups. Yeah, finding changes of interest, false discovery control, this is how we deal with multiple testing. We want to limit the number or proportion of false positives. That means among our findings, we don't want to have more than 10 or maybe 5% or 10%, whatever, false positives, so that the risk of picking wrong spots and identifying them is limited. Let me also mention here already that you should avoid Bonferroni correction. Bonferroni correction is just kind of a certain simple correction, and there are better ones which are more intelligent, if we would call it like that. If we can call an algorithm intelligent, then there are others. Let me show this now in Delta 2D. So first, let's have a look at the t-test. I open this t-test dialog. Let me make it a little bit smaller, like this. And then we have here a list of the groups. We can scroll down, and then we have to select now two groups that we want to compare with the t-test. For example, let's take treatment 160 minutes as group 1 of our t-test, and treatment 360 minutes as group 2. Then we want to use a certain p-value. 0.001 is very strict, but it should be good, like this. And we want to use p-values based on permutations. I will explain that within a few minutes. P-value of 0.001 means that without any false discovery, we can expect among 1,000 expression profiles to get 10 false positives. Just by random, 10 will meet our p-value criterion. So that is why we need p-value force discovery corrections, and we can limit this to these 10, or we can limit it to a certain proportion among our findings. Let's limit it to maybe 5, like this. And then let's also choose hierarchical trees. I confirm this clustering, and then you will get a certain result. It will be clustered also. Here we go. And we have just 5 expression profiles. We said we want to have a maximum of 5 false positives, so that is now a nice moment to make you aware of the fact that statistical analysis just provides guesses, estimations, hints. These expression profiles might be interesting, but they are not necessarily interesting. They might be false positives, but they are not necessarily false positives. So it might make sense to now follow up these spots and then decide whether these 5 spots match your biological theory. Of course, I hope that you will get more than the 5 ones that might be false positives, maybe 20 or 30, so that you think, okay, I now found 30 expression profiles. 5 of them might be false positives. So let me, I don't know which of them, so let me just identify all of them, and then I will publish all those where I think that I can provide a good argumentation, good reasons for publishing them. Not only quantities, but also biological theory. Coming to then maybe an ANOVA analysis. Let me show ANOVA 1 analysis. If you have a number of groups, for example 3 groups, since you have 3 points in time, let me then have a look at the 3 points in time of the treatment 2. So treatment 2 0 minutes should be group 1, 30 minutes should be group 2, and 60 minutes should be group 3. We again choose p-values based on permutations. And then we choose again 001, and for discovery rate control we want to have a maximum of, well, let's say again 5. I would also like to construct a hierarchical tree. Press OK, confirm my clustering here. These are settings that we recommend: Euclidean distance and complete linkage clustering. I press OK, the permutations are calculated, and then we will see the finding in our example window here. It will be a new branch for ANOVA. Here we go, getting a clustered view like this. Here we have a number of significant expression profiles. Among them will be 5 false positives. We don't know which of them, but now you can continue analyzing the different clusters, why they are different. And it's nice to observe these blocks here. I hope that you can see some differences in intensity, and that these clusters form certain spots and blocks where the spot quantities really change between the clusters. Of course, you have to know what you're looking for, which changes are of interest between cell lines, between points in time, between which combination of cell lines and points in times. So this is completely up to you, and then give a good reason for your publication. Now let's continue with my presentation. The bell-shaped data is something that we expect, but do we know that the data is really bell-shaped distributed? You could now say, well, it doesn't matter, but in fact it matters, because t-test, ANOVA, and two-way ANOVA or two-factor ANOVA depend upon the fact that the data is bell-shaped distributed. If that's not true, or, which is commonly true, we just don't know whether the data is bell-shaped distributed, then you should stay on the safe side and look for alternatives. One alternative is using the t-test with permutations. This is a flavor of the t-test which does not demand this bell-shaped distributed data anymore. It is then more a rank-based analyzes, and it's a certain flavor of the t-test with some changes. The p-values are not the same p-values as before, and it depends upon the possible number of permutations what you will get then. However, it's better to do this rather than to get results which do not match their preconditions. Another alternative for non-bell-shaped data, or just not known how shaped data, are non-parametric tests. For example, Wilcoxon-Whitney, Kruskal-Wallis, Max-Killing's test. They are alternatives to the t-test, ANOVA, or two-factor ANOVA, respectively. And finally, I would like to show you how you can find expression profiles that look similar to a certain template. This is done with Pavlidis template matching, and you can define a template by just creating one manually, since you have a certain idea how an interesting expression profile should look like. Or use an existing profile. Maybe you have seen a publication where a certain protein spot, which you know on your gel, which spot it is, that this is involved in your processes and you want to look for similar expressed proteins, or you just use the average of an existing cluster, an interesting cluster. So Delta 2 will then find those expression profiles matching this template. Let me show this now in Delta 2D. I have already shown the t-test with the permutation-based t-test. Please remember that the p-values then will be different. By the way, in all these branches, result branches here, we not only have these nice looks or displays of heat maps, we also have table views for the significant ones and for the non-significant ones as well, where you get the group means and, for example, also the raw p-value and the false discovery rate, or other values depending upon the test, of course. Now let's have a look into non-parametric tests. I would like to give a demo of the Max-Killing's test, which is the equivalent to two-factor ANOVA. I press next, and then we can give the two factors names. I call the first factor treatment and the second factor time, and we have for the treatment 4 levels and for time 3 levels. The first level for the treatment is a control cell line, the second one a treatment 1, a treatment 2, and the fourth a treatment 3 cell line, while the levels of time are 0 minutes, 30 minutes, and 60 minutes. Then you can see that we have now a table including the images, and then treatment and time as the two factors. Here on the top we can see that. And now I could just take the image and place it here. This image belongs to time 0 minutes and treatment control cell line. I can do this now with all the different images, which is, well, some clicks, but I have prepared that and I can just load these assignments as we can save the design assignments. So if you have once done all this assignment, you can save this design and load it again if you want to repeat the same test, maybe with another p-value or other different settings. So let me load this. I get it from my desktop in this pool data. I load this, and now all this assignment is done. We have 4 replicates for each factor combination. Then I can press next. I choose a certain critical p-value, an alpha like this. I want to get the results clustered and click execute. I confirm my clustering method and then get result here. We have a different parts now, different views on our results. Treatment significant genes, treatment non-significant one, time significant, and so on. So it depends upon what you want to learn, which of the views you can open, and then there are treatment significant genes and time significant genes here inside, and you can then also find with some operations that you can learn about in the manual how to combine these and find those expression profiles that belong to both. You can also view that as graphs for the significant, the time significant, and so on. So a lot of different views, and it's up to you what you're interested in, where you want to focus on. Furthermore, I would like to show Pavlidis template matching now. This is the Pavlidis template matching window, and you can now, for each image, for each image we have a slider here. I can scroll to the right so that you can see this is 48 images. Those of you who can count quickly can do that. And you can also deactivate the slider for a certain filter, and then the values of these images are not considered when comparing expression profiles with the template. So they are masked, not taken into account then. Otherwise, you can then also move the sliders from small values. This is standardized from 0 to 1, minimum and maximum, and then you can just have low expression levels and high expression levels on the certain images. And this can be done for all the 48 images, of course. You can also take a certain expression profile where you know that this is an interesting protein, for example this one, and take this as the pattern, as the template. Of course, you can take this and then improve it if you think it could be improved and being clearer than this expression profile is, to remove the noise, for example. And then we can enter a p-value again, choose for constructing hierarchical trees, and say OK, confirming our clustering parameter dialog. And then we get results again. PTM, Pavlidis template matching, matched genes. Here we have the template on the top. This is a certain protein that we have used as the template, and all the others match the dynamic of this template. Hierarchical trees are also available, and then you can see how these expression profiles are clustered and identify the structures within these findings. So I hope you could see there's a lot of flexibility in the statistical analysis with Delta 2D. You can do very much. I would like to give the take-home message: be aware of the preconditions of each test. Check your data, whether these conditions are fulfilled or not. If you don't know, stay on the safe side. Only use tests where you know you can apply them. Then be aware of multiple testing, of course. Do false discovery rate control. And also be aware that you need a minimum number of replicates.